So, we will continue with the discussion on normal shock. So, I have a numerical problem here in which I have a CD nozzle. So, this is supplied from a chamber where the pressure is 450 kilopascal. There is a normal shock somewhere which is 20 cm square. The area at the exit is 30 centimeter square. Area at the throat is 12 centimeter square. And the shock happens at a area where it is 20 centimeter square. Find Py, Pe, Ay star, and Mach number at the exit. Okay. So, I have a nozzle, there is a P0 that is being supplied. So, you have a P0, nozzle comes, the throat area is given, exit area is given, and there is a shock that is sitting at a location where the area is 20 centimeter square. Okay. So, this is some case where what we had seen, which we are going to discuss it in the next week lecture. It is going to be some back pressure between P critical 1 and P critical 3. So, the back pressure is somewhere here. So, that there is a shock that is happening here. Okay. So, so the question is to find the exit pressure Py, that is after the shock, and this. Now, in this question we know that the shock is going to happen only for a supersonic flow. Okay. So, that is the first question, first information we have from here, shock for a supersonic flow, which means throat is shocked, or the Mach number at the throat is 1, okay, which implies your A throat is your A star. Now, this is before the shock, so I will also use the suffix x. Okay. So, just before the shock, I have an isentropic flow. After the shock, I have isentropic flow. Only the shock is the non-isentropic flow. So, I will use isentropic tables up to this just before the shock, and isentropic tables just after this the shock, and for the properties across the shock I will use the shock tables, which is a non-isentropic process. Okay. So, I have the throat Ax star equals At equals 12 centimeter square. Shock happens at a location 20 centimeter square. Okay. So I can find AS by AX star, which is 20 by 12. So AS by AX star is 1.67. This, as we know, is going to give me two Mach numbers, M and A by A star. I will take a supersonic Mach number because the flow is now supersonic, it is chalked. So, the Mach number associated with this is 1.99 from isentropic tables. Okay. So, I look at the tables, I get A by A star of 1.6, A by A star of 1.6, 1.67 to be 1.99 from the isentropic table. So, this is the Mach number here at the just before the shock, which is my mx. Okay. So, I can get all the properties at mx using my isentropic table. Okay. So, I take the isentropic table, 1.99 will give me T by T0, P by P0 all at x, okay, before the shock from isentropic tables. Now, the question is to find the properties across the shock. So, my P by P0, Px by P0x is Px by P0x is, I take the tables 1.99, Px by P0x is 0.129. Okay. So, my P0x is already given. So, my Px is 0.129 into 450 kilopascal. Okay, that is my Px. How much? 58.05 kilopascal. Okay. So, now I have mx, which is 1.99. So, I look at my shock tables to get my my, which is 1.99. 1.99 is not given in the shock tables here. So, I have values at 1.98 and 2. The mx is 0.581, 0.5771. So, ideally you need to interpolate this. So, now let us take the average. So, this would be 0.579. Okay. So, that is my my. Now, the moment I have my my, I can also get the pressure jump Py by Px. Py by Px is again the pressure values are, pressure jump values are 4.407 and 4.5. So, the average is 4. Approximately this. Okay. Again Ty by Tx as Ty by Tx is 1.671, 1.687. So, the average is around 1.679. Okay. So, from this I can find my Py, and then I can also find P0 y. Where is that? Okay, so we haven't. So I will rub this. So my P0 y by P0 x is again the average of these two values here. So it would be 0.7 to 6. Okay. So I have a shock here. There is a P0x that is coming. So it would be constant up to the shock, and after this I again have a P0y. Okay. So the jump P0x by P0y is given here. P0x is already given as 450 kilopascal. So my P0y is 0.726 into P0x. In P0x is for 450 kilopascal. Okay. 3. .326 point something kilopascal. Okay. Now we also know that P0x Ax star equals P0y Ay star for a non-isentropic process. We know P0x is 450 kilopascal, Ax is our A throat, which is 12 centimeters square. P0y is again in kilopascal, so it is convenient to write this into Ay star. So my Ay star is 16.53 centimeter square. Okay. Now we know your Ay star as 16.53 centimeter square. We know our A exit to be 30 centimeter square. Okay. So in the nozzle I have a shock here. There is a Ax star associated with this, which happens to be our A throat, and this after the shock we have a reduction in increase in our A star value, which is a new A star. Now there is a area that is given here. Okay, A exit. So up here again is isentropic, this is isentropic. So all I need to do is this area ratio, find the corresponding Mach number. So A exit by A y star is 30 centimeter divided by 16.53. This is 1.815. So the Mach number associated with this as 1.815. Is 1 m is approximately 2.31 or no. I have looked at the wrong table. A by A star 1.85. 1.85 is 1.81 is around 2.08 or around 0.32, 0.34. Okay. Now the question is, which one will you pick? Okay. So now I have a strong normal shock, after which I have a subsonic shock. Now this subsonic shock, I still have a diverging section. Subsonic flow, yes. Yeah, so I have a supersonic flow, I have a shock, after which I have a subsonic flow, and the subsonic flow faces a diverging section, so it continues to be a subsonic flow. So your answer would be this. So your M exit is going to be this. M exit is this. So that is the Mach number here. Now the moment you have the Mach number, you already know your P0 y, which is your stagnation pressure here. You can easily find your P exit. P exit from the, look at the isentropic tables, find the associated value of P exit. So your P exit is okay. So you look at the isentropic tables and get the fraction, which is M exit is 0.34, 0.34, P by P0 is 0.92, 0.92. So this is an approximate value because you have to interpolate and get it. Okay. So you get this ratio as P exit by P0y. So your P exit is 0.923 into P0y, which we have obtained it before. So you get your P exit. So the original problem we had supposed to find Py, P exit, Ay star and Me. So we have obtained all those quantities. If one temperature or velocity is also given, you could find the other temperature quantities also. Okay. So, for that we need at least one temperature or one velocity, okay, because the Mach number is already given. Okay. So, we will end with one more problem on say pitot tube, and then okay. So, I have a shock that is standing before a pitot tube. Some measuring device, go to some transducer or a U tube or some quantity, okay, say let us take U tube, some instrument. So, this is going to pressure my P0, this is going to measure my P static. But if the flow is oncoming flow is greater than 1, you are going to have a shock in between. So, assume normal shock. Okay. So, what is measured here is P0 is 190 kilopascal, P static is 150 kilopascal, your T0 is 400 Kelvin. Find the Mach number. So, let us say M1, find M1. So, a supersonic flow is coming and you have a measuring device here without static tube. Because it is supersonic flow, this bluff body will create a shock. So, that shock is standing in front, and let us assume this to be a normal shock, and because of which you have to compute M1 in terms of the properties that jump across the shock. Okay. So, your P0 y is 190 kilopascal, because that is the stagnation pressure after the shock. So, that would be, this is after the shock. So, your static pressure after the shock is given as 150 kilopascal. Okay. So, your P0y by Py is 190 by 150 kilopascal. 1 kilopascal cancel. So, this would be around 1.267. So, you look at the isentropic tables. Find your My. So, for this particular ratio, this is from your Py by P0y by Py is 1 plus gamma minus 1 by 2 My square to the power gamma by gamma minus 1. Okay. Or use your isentropic tables to find the Mach number My, that is after the shock. So, My for this particular ratio is what? 0.59. So, that is your Mach number after the shock. Okay. The moment you know Mach number after the shock, you know the relation in terms of Mach number before the shock, or you use your shock tables. So, using the shock tables for my equals 0.59 gives me an mx of my 0.59 0.59 mx is 1.86. Okay. I have looked at the wrong gamma table. So 0.59 is 1.92. Okay, for gamma equals 1.4 shock tables. Now, if I have this Mach number, that's that's the question. So your mx is or m1 is 1.92. Okay. So, so you can write, technically you can write your mx in terms of p0 y and py. Okay. So your mx is a function of p0y and py. So if I have a pitot tube, pitot static tube, I measure p0y and py, p0y and py, I can directly get px if I know this function. Okay, that you can try it out. Write your mx in terms of p0y and pa. Okay, in fact that is something called a Rayleigh equation for pitot tube, where your Mach number that is to be measured or the Mach number of the oncoming fluid in terms of the values that is being shown in the pitot tube, pitot static tube. So pitot static tube, the value that is shown in the pitot static tube is p0y and py, from which you can directly get your Mach number of the oncoming fluid. Okay. So with this, for the time being, we will end the normal shock discussion. Next class we will take up CD nozzle and do the same set of analysis, see what happens, and also do the some numerical problems involving shocks in the diverging section of CD nozzle. Okay. We will also discuss the over expansion and under expansion of the nozzles. Okay.